All right, in this video, we're going to talk about suggested homework from section 9.9 with representation of functions by power series. Remember that a power series can exactly represent a function, whereas a Taylor polynomial or Maclaurin polynomial can only approximate the function near its center C. So let's go ahead and look at number 5. F of x is equal to 4 over 3 plus x. So there's a rule for power series that says that they can be written as a geometric series if they are in the form of summation of, if the function is in the form of s is equal to a naught over 1 minus r, then this is s is equal to summation n equals 0 to infinity of a naught times r to the n. So you remember that we're kind of going backwards from what the summation of the geometric series was. If it's written as a rational function like this, let's try and make it match that. So I need to make sure that there's always a 1 here in the formula. So I'm going to divide everything by 3. F of x is 4/3 over 1 plus x over 3. And now I need to write this so that it's minus something. So f of x is 4/3 over 1 minus a negative x over 3. So this is the summation from n equals 0 to infinity of 4/3 times a negative x over 3 to the n. So that's pretty straightforward. If you want to separate the 1 from the n, the negative 1 to the n from the x over 3, you can do that. This one is going to be centered at 0 because that's the x value that's going to make that factor there 0. All right, let's look at number 9. 9 says, find the power series for the function centered at C and determine its interval of convergence. So 9 says f of x is equal to 1 over 1 minus 3x, centered at 0. So I have summation n equals 0 to infinity of 1. Then I have 3x to the n. So absolute value of 3x is less than 1. 3 absolute value of x is less than 1. Absolute value of x is less than 1/3. So r is equal to 1/3. All right, let's look at 13. F of x is equal to 2 over 5x plus 4, 2 over 4 plus 5x. Divide everything by 4. F of x is equal to 1/2 over 1 plus 5 force x. And then this is going to be 1/2 over 1 minus a negative 5 force x. So this is summation n equals 0 to infinity of 1/2 times negative 5 force x to the n. Now they want me to center that at -1, so let me go back and fix this here. If I'm centering at -1, I need x plus 1 to show up in the problem. So this is 5x plus 5 minus 1 is equal to 2 over 5 times x plus 1 minus 1 is a -2 over 1 minus 5 times x plus 1. And that is going to be summation n equals 0 to infinity, -2 times -5 x plus 1 to the n is a n equals 0 to infinity, -1 times 2 times -1 to the n times 5 to the n times x plus 1 to the n. I'm going to try and put all the -1 things together. So this is -1 to the n plus 1 times 2 times 5 x plus 5 to the n. Pull the 2 all the way out there. And what was I supposed to find? Interval of convergence. So absolute value of r has to be less than 1. 5x plus 1 has to be less than 1. Absolute value x plus 1 has to be less than 1/5. So r has to be 1/5. Interval is x plus 1 is between -1/5 and 1/5. And subtract 1 is -6/5. Less than x is less than -4/5. And test that in the original up here. So -6/5 is a -1 to the n, which is a -1 to the 2n plus 1, is a odd number, and so that's always a -1. So that would just be a whole bunch of -2's added up, which would go to infinity, -4/5. So 1 to the n, that would go away. A -1 to the n plus 1 times 2, that would be alternating back and forth, +1, or +2, -2, +2, -2. That would also not converge because the nth term isn't going to 0, it would be going to 2 or -2. So interval of convergence would be -6/5 to -4/5. Again, 13 said I needed to be centered at -1. If it didn't say that, then I wouldn't try to make that happen, and things would have been a lot easier. Let's look at number 19. 19 says that h of x is equal to a -2 over x squared minus 1. which they've done the partial fraction decomposition for us, is 1 over 1 plus x plus 1 over 1 minus x, which both can be written geometrically. This is the summation from n equals 0 to infinity of negative x to the n, plus, and this one is summation n equals 0 to infinity of x to the n. So this is going to be, when I put these together, this will be 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth plus so on and so forth. And this one is going to be 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth plus so on. When I add them together, this is 2. That term cancels, plus 2x squared plus 2x to the fourth, so on. And I'll have 2x to the 2n, right? So this is going to be 2 summation n equals 0 to infinity of x to the 2n. And that means that the absolute value of x squared has to be less than 1. And so this is going to have to be that x squared is between 0 and 1, but x is going to have to be between negative 1 and 1. And if I would test my endpoints here, that negative 1 squared is 1 to the n, that's divergent. 1 squared is 1 to the n, would also be divergent, so it doesn't converge on either end. We have the open interval of convergence, negative 1 to 1. Let's look at 23. 23 says f of x is equal to ln of x plus 1 is equal to integral 1 over x plus 1 dx. So the formula for ln of x, I think we're supposed to use the table use power series that 1 over 1 plus x is equal to n equals 0 to infinity, negative 1 to the n, x to the n for absolute value of x is less than 1. So if I integrate both sides, which is what it looks like I'm doing here, ln of x plus 1 is going to be equal to the integral summation n equals 0 to infinity, negative 1 to the n, x to the n. And this is going to give me just the x part increases here. So this is negative 1 to the n, x to the n plus 1 over n plus 1. summation n equals to 0 to infinity here. That makes sense. It would start at x to the first instead of x to the 0 power because I integrated. And my interval of convergence here is limit as n goes to infinity of x to the n plus 2 over n plus 2 times n plus 1 over x to the n plus 1. This limit as n goes to infinity of n plus 1 over n plus 2, absolute value of x less than 1. So absolute value of x is less than 1. X is between -1 and 1. Come back up to my series here. And if I put in -1 to the n plus 1 times -1 to the n, that's -1 to the 2n plus 1 is -1 over n plus 1 is a divergent series that's related to the harmonic series. So it does not converge on the left-hand side. If I stick in 1, 1 to the n plus 1 goes away, -1 to the n over n plus 1. That is going to be conditionally converging because the limit of the nth term goes to 0, and it's a decreasing series. So this gives an interval of convergence of -1 open on that side to 1 closed on that side. So that was number 23. Let's look now at number 39. And we're to use this same old power series here. Use 1 over 1 minus x is equal to the summation n equals 0 to infinity of x to the n, with the absolute value of n less than 1. We want to be centered at 0. So f of x is equal to 1 plus x over 1 minus x quantity squared. And that's going to be equal to 1 over 1 minus x quantity squared plus x over 1 minus x quantity squared. So let's just deal with this first part here as the derivative, or almost the derivative, of one minus x to the negative first will be equal to a negative 1 minus x to the negative second times the derivative of the inside is -1 will be a positive 1 over 1 minus x quantity squared, which is what I have. I have the exact derivative of this function here. So let's take the derivative of both sides. And so that means 1 over 1 minus x quantity squared is going to be equal to the derivative of this side as summation n x to the n minus 1. Well, I need to start at the 0 power here. I can't have a negative exponent, so I have to bump my n up from 0 to 1 for that to work. And then I'm going to multiply by x to get the second piece here. So x over 1 minus x quantity squared is equal to summation n equals 1 to infinity of n x to the n minus 1 plus 1 is going to be x to the n. Now I want to add those series together and do a little bit of math that may seem magical to you, but I'll explain what I'm doing. This is important to do for differential equations when we get series solutions there. So I'd like both of my terms to start at the same power and to start at the same index. So if I can bring this index down to 0, that brings all of these n's up by 1 on the inside, so that this becomes an x to the n. Why do I want to do that? Because now this is x to the 0, x to the 1, so on. That's a regular power series. And I had to start with 1 here, so 0 plus 1 is 1, and 1 minus 1 was 0, and this starts with 0 here. Now with this one here, this is a little trickier to see what I'm going to do, but if I go down to n equals 0, that doesn't change the value of the series at all because I'm multiplying by 0. Adding 0 doesn't change anything, so I'll go down to 0 here and x to the n. So that gives me a single series n equals 0 to infinity of n plus 1 plus another n x to the n. So add your like terms here, n and n plus 1 will make n equals 0 to infinity of 2n plus 1 and keep the common power, base and power there of x to the n. And the absolute value of x is going to have to be less than 1 for my convergence here. That's it for this video. We'll come back next time and talk about section 9.10, which will wrap up our discussion of chapter 9. We'll talk about Taylor and Maclaurin series, specifically Taylor and Maclaurin power series representations of transcendental functions that are things like sine, cosine, e to the x, ln of x, so on. We'll have a known list, and also how do we generate those series ourselves. As the power series with an infinite number of terms, we already talked about doing nth degree polynomials for them to approximate, but how do we get exact representations of functions as these Taylor or Maclaurin power series? Super important for our series solutions for differential equations. So I'll see you for the next video.